everybody. All right, in this video, we're going to recap what we discovered today in class about continuity. So remember, before today, we had a somewhat informal definition of continuity where we said a function was continuous if there were no holes in the graph or there were no breaks in the graph, like a vertical asymptote. And then we also said if you could draw the graph with a pencil, you would never have to pick up your pencil. So that was like an informal definition. Well, as you can see, limits give us a more formal definition of continuity. So now we can determine if a function is continuous at a point by looking at limits, evaluating limits, and then also evaluating the function at that value of x. Okay, so these are the three conditions that have to be met for you to be able to justify or say, yes, a function is continuous at a given point. So function f is continuous at c, meaning x equals c, when these three conditions are met. F of c is defined. The limit as x approaches c of f of x exists. And most importantly, they equal each other. So the limit as x approaches c of f of x equals f of c. Now, remember, to justify that the limit exists, because this is a two-sided or general limit, if you're given a piecewise function, then you have to find the limit from both sides, meaning evaluate the one-sided limits. Okay, so my advice would be on a question, just go through your three steps, one by one, okay? All right, here's an example. Piecewise function for f of x is below. Is f of x continuous at x equals 2? Justify your answer. You have to go through the three conditions, and you have to use proper notation, okay? So condition 1, we're going to find f of 2. Well, remember, when we're evaluating a function, we're answering the question, what is y equal to when x equals 2? So in that case, we would plug into the 5x minus 7 because f of x equals 5x minus 7 when x is greater than or equal to 2. Okay, but we're just going to plug in 2 for x. And so 5 times 2 is 10, minus 7 is 3. Okay, that means condition 1. F of 2 is defined, it equals 3. Okay, condition 2, we have to evaluate the limit as x approaches 2. But again, because this is a piecewise function with inequalities, we're going to have to evaluate our one-sided limits. Okay, so the limit as x approaches 2 from the left of f of x, well, in that case, we would be looking for values less than 2, so we're going to plug into this piece. So this will equal 2 squared plus 2 minus 3, which ends up being 4 plus 2, which is 6. 6 minus 3 is 3. Okay, then we have to evaluate the limit as x approaches 2 from the right, which again, from the right would be values greater than 2, so we're going to plug into the 5x minus 7. We already know we're going to get 3 for that. Okay, now, because our one-sided limits are equal, we can now say condition 2 is met. The limit as x approaches 2 of f of x equals 3. Okay, so that's condition 2. We can check it off. The limit does exist. All right, condition 3 also checks off because the limit as x approaches 2 of f of x equals f of 2. Because remember, we got 3 for all of these. Okay? Okay, so how do we write our final answer? My best advice on questions like this, because this would be like a free response question, is just like repeat the question, okay? The question was, is f of x continuous at x equals 2? So we're going to say f of x is continuous at x equals 2, and then the justification, because, and that's our money statement right there, condition number 3, a limit as x approaches 2 of f of x equals f of 2, period. Okay, and you've got all the work above it to show, that they are equal. Okay, now, sometimes you'll be given a question like this. The piecewise function for q of x is below. Find the value for a, little typo there, that makes q of x continuous at x equals 1. Well, think back to what we had to do in the previous problem. To justify continuity, we had to find f of 2, we had to evaluate the limit as x approaches 2, and we had to make sure they equal each other, okay? So basically, here we would be saying that the limit as x approaches 1 of q of x has to equal f of 1. Well, remember, to evaluate the two-sided limit, you have to evaluate your one-sided limits, right? And in that case, we want to make sure that the pieces equal each other. So that's like saying x minus 3 has to equal x squared plus ax minus 5 when x equals 1, because f of 1 means you're going to plug in 1 for x, okay? So when x equals 1, this will become 1 minus 3 equals 1 squared plus a times 1 minus 5. Simplify, we get negative 2 equals 1 plus a minus 5. Then we get negative 2 equals, well, 1 minus 5 is negative 4, so a minus 4. And then we can just solve for a. We're going to add 4, and we get 2 equals a. Okay, so long story short, you want to set pieces equal to each other. And plug in, well, in this case, we plugged in 1 for x. Okay. And then solve for a. Depending on whatever x is equal to, that's what you would plug in for x. So, if this was a different value of x, then you would just plug that in for x. But it's just another way to say that, this is basically what would have to happen for the limit as x approaches 1 to equal f of 1. Okay? But on these questions, the shortcut method is set the pieces equal to each other and plug in whatever x is equal to for x, and then just solve for the variable. Okay, so this kind of leads us to, well, what happens if a function is not continuous at a point? Well, there are 3 different types of discontinuities. So if we're saying a function is not continuous at a point, then we're saying it's discontinuous at that point. And there are different scenarios that could happen, and of course they all have special names. But they fall into 2 categories. Your discontinuities fall into 2 categories: removable and non-removable. Okay, so we're going to look at the non-removable first, because there are 2 non-removable discontinuities. The first one is what we would call a jump discontinuity. And well, I want to start with a graph, because we saw this happen quite a bit today in class in our exploration. So remember, we had a jump discontinuity, anytime there was literally a jump in the graph. So maybe we had an open circle and then a closed circle right above it, something like this. Now, instead of a possible equation, I actually want to give you a justification. So as you're going through your 3 tests for continuity, if you have a jump discontinuity at x equals c, then you'll be able to find f of c, because that would just be the closed circle. But what's going to happen when you go through the 3 tests is that the limit as x approaches c of that function does not exist. And why does it not exist? Because your left-hand limit does not equal your right-hand limit. So in that case, if you were going through your 3 tests of continuity, once you evaluated your one-sided limits, you would get 2 different values. Okay. All right. The next non-removable discontinuity is what we call an infinite discontinuity, which essentially is
Teachers, please pardon the interruption. At this time, can you please release the students that needed the digital lesson number 2 to the auditorium? Digital lesson number 2 to the auditorium.
All right, so an infinite discontinuity is essentially a vertical asymptote in the graph, okay? So maybe your graph might look something like this. Again, if you were going through your 3 tests of continuity, you would get to number 2, and you would find that the limit as x approaches c of f of x does not exist. Now remember, you might be able to answer that limit with infinity or negative infinity, but that technically means the limit does not exist. So in this case, if you're testing for continuity, you could stop right there and say that the function is not continuous at that point because the limit does not exist or because there is an infinite discontinuity. Okay? All right, now our third type, which is considered removable, is what we call a point discontinuity. Okay, so a point discontinuity graphically is going to be a case where your limit exists, but there's still an open circle or a hole in the graph, so something like this. So if you were going through your 3 tests of continuity, for this one you would get all the way to test number 3, and you would find that the limit as x approaches c does not equal f of c. Okay, so in this case it would fail the 3rd test. Now as far as non-removable or removable goes, I kind of think of them as maybe like the severity of the discontinuity. So removable would not be as severe as non-removable. So like your jump discontinuity and your infinite discontinuity are like more severe than your point discontinuity. All right, let's look at a few examples. We're going to start with a graph. So here, we're given the graph of f of x. We want to determine all x values where f of x is not continuous, and then just classify each as removable or non-removable. So I tend to just read the graph from left to right. So as I'm reading from left to right, I can see that there is a jump at x equals -1. And remember, a jump is considered non-removable. All right, continuing on, I can see that there is a vertical asymptote at x equals 1, so that would be an infinite discontinuity, which is also non-removable. All right, continuing on, we have a hole in the graph when x equals 3. So remember, a hole is called a point discontinuity, which is considered removable. And then continuing on, we also have a hole when x equals 5, which is also a point discontinuity, which again is also removable. All right, so usually graphically, the discontinuities are pretty easy to find. You just have to remember their special names, jump, infinite, point, and then whether they're removable or non-removable, which only the point discontinuity is removable. Okay, now, questions like this might be a little bit more difficult where you're given an equation. So here we want to list the x values where g of x is not continuous and classify each type. Most of the time, you're going to be given a rational function because your rational functions are the functions that have vertical asymptotes in their graphs or holes in their graph. You might also be given a piecewise function, and because with a piecewise, that's when you might have a jump discontinuity. So usually when you're given a rational function, you're just trying to find the holes and the vertical asymptotes. So we usually would start by factoring. So if we factor the numerator, we're looking for factors of -40 that add to 3. So +8, -5 would work. Factor the denominator, we're looking for factors of -10 that add to -3. So -5, +2 would work. And then I'm noticing that we could simplify this because we have x minus 5 over x minus 5. Now, if you guys think back to your pre-cal days with rational functions, anytime you have factors the same top and bottom, that indicates a hole in the graph at x equals 5. It's always at the 0 of that factor. Okay, so that's how we might have answered it back in pre-cal, but now that we're in calculus, we're going to say that g of x has a point discontinuity at x equals 5. Okay, now because x plus 2 is still in the denominator, that means that the graph has a vertical asymptote at -2. Okay, and so that's how we would have said it back in pre-cal days. We would say that g of x has a vertical asymptote when x equals -2, but now in calculus we're going to identify this as an infinite discontinuity at x equals -2. Okay. And you guys remember with your rational functions, the discontinuities are going to occur whenever the denominator is equal to 0, because that's when the function is undefined. And so that's why we have discontinuities at 5 and -2, because those would be the zeros of the denominator. Okay? But then you can identify them more specifically as a hole and a VA, or a point discontinuity and infinite discontinuity. Okay, now, let's look at this example. Ooh, look at that piecewise. All right, so here we're given h of x, which has 4 pieces, and we want to determine all the x values where h of x is discontinuous and then classify each as removable or non-removable. So with your piecewise functions, this is when you may have a jump discontinuity, because the idea is, do the pieces meet or do they not meet, meaning there's a jump. Well, with your piecewise functions, the jump would possibly occur at what I call the cutoff points. So these are basically your cutoff points, where the function changes, okay? So, don't know what I'm writing there. All right, so anyway, we need to consider x equals -2, x equals 1, and x equals 3. Okay, these are what I would call the cutoff points. Or those are the values of x where we might have a jump discontinuity. So how do we determine if we have a jump? You to evaluate your one-sided limits. So, let's just jump right in. Let's start with -2. We need to evaluate the limit as x approaches -2 from the left, which means we're going to plug into the 2x minus 1, and that ends up equaling -5. And we're going to find the limit as x approaches -2 from the right, which means we're going to plug into the x squared minus 9, and we're going to get -5, which leads us to the conclusion that the limit as x approaches -2 of h of x equals -5. Well, we know the limit exists, so let's just find h of -5. I'm essentially going through my tests of continuity. So h of -5, again, we would plug into the x squared minus 9, and so we already know that's going to equal -5. So what I have discovered here is h of x is continuous at x equals -2. So there is no discontinuity when x equals -2. Okay, let's try x equals 1. Okay, we have the color here. So again, start with your one-sided limits. So we want to evaluate the limit as x approaches +1. I keep wanting to throw a negative sign in front of that 1. As x approaches 1 from the left of h of x. Okay, which means we are going to plug into the x squared minus 9. So 1 squared minus 9 equals -8. Okay, evaluate the limit as x approaches 1 from the right, which means we're going to plug into 3x plus 2, which equals 5, which tells me the limit as x approaches 1 does not exist, and I also know that there is a jump discontinuity at x equals 1. Okay, let's try x equals 3 now. Hopefully I can squeeze this in and still see the function. Nope. There we go. Okay, so we're going to evaluate the limit as x approaches 3 from the left of h of x, which means we're going to plug into the 3x plus 2, which equals 8. And then we're going to evaluate the limit as x approaches 3 from the right, which means we're plugging into the 4x minus 1. That equals 11, so I can already tell that we have a jump.
Teachers, pause the interruption. At this time, please send any seniors that have not received their Chromebooks to the Media Center. Any seniors that have not received their Chromebooks to the Media Center. Thank you.
We have a jump discontinuity at x equals 3. And remember that your jump discontinuities are non-movable. We should go back and add that, because that was part of our question. Trying to do the colors.